Hi, this is lecture 12 for Chem 223. Today we'll be talking about redox reactions, galvanic cells, and a little bit about standard reduction potentials. And this will actually be our last lecture that comes with a handout. So I'll show you that real fast. Just looks like this. It's got a few practice problems similar to the other handouts. So go ahead and print that out and work through it. Of course, that'll be a part of your reading quiz this week as well. Now let's jump back over to our PowerPoint. Let's start out with a little video. So this is a video of zinc metal in a copper sulfate solution. Notice that a quick dip in there causes it to get plated a little bit. What happens if we leave it in there for a long time? Let's speed up the time here a little bit. Right, now let's go ahead and pull it out, see what it looks like now. Gross, right? Well, that stuff's just falling right off of there. Yeah. Right, now a lot of you with electrochemistry are probably feeling like this. A middle-aged dad in a haunted house being terrified, screaming your lungs out. Okay, but by the end of today's lecture, or at least by the end of our lectures about electrochemistry, you'll be looking more like this. Confident, sure of yourself, and also now a woman. All right, but let's look at a more molecular view of what's going on here. Let's have some copper ions floating around in solution, and we've got our zinc bar over here. So as your ions float around, sometimes your copper ions will get close to your zinc plate, and that zinc plate will shoot off some electrons into your copper. Now when you change the electronic structure of copper from its 2+ state to its neutral state, you change its color from blue to orange. And why is that? Well, it's because you're affecting the electronic configuration of that ion. And zinc, of course, is metallic-y, that silver color when it's a solid, and generally colorless when it's in an aqueous solution. If you get it concentrated enough, it'll look cloudy, but generally it just looks colorless. All right, so this is an oxidation reduction reaction. Let's look at it in just a simple chemical reaction form here, right? We have zinc reacting with copper 2+ to form zinc 2+ and copper. And of course, the zinc starts as a solid, ends as an aqueous substance. The copper starts out as aqueous and ends up plated as solid. Now, which ones are getting oxidized and what's getting reduced? Well, let's turn back to our old friend, the acronym. And the acronym we'll be using here is Leo says GER. So Leo says GER is short for loss of electrons is oxidation, and gain of electrons is reduction. All right, so the zinc species is losing electrons. So that loss of electrons means it's being oxidized. And the copper 2+ is gaining electrons, which means it is being reduced. Another acronym that you can use if it's more helpful is OIL-RIG. I actually prefer OIL-RIG. But OIL-RIG stands for oxidation is losing electrons, reduction is gaining electrons. So it's the same as Leo says GER. I just like it better. All right, so now that we've talked about what's getting oxidized and what's getting reduced, let's talk about oxidizing agents and reducing agents. So here in this reaction, we have silver plus reacting with copper. So copper is losing electrons and going to copper 2+. So it's being oxidized, and the silver plus is gaining electrons, and it is getting neutralized, or it's getting reduced. So in this case, what is the copper metal? So the copper metal, since it is giving up electrons, it is the reducing agent. So even though it's getting oxidized, it is reducing the silver. So we call copper a reducing agent or a reductant. Likewise, since the silver is taking electrons from the copper and causing the copper to be oxidized, the silver is what we refer to as our oxidizing agent or our oxidant. All right, so try and remember those rules. And now let's put this into a half cell configuration like you've seen before. Here, of course, we have our solid zinc bar in a zinc sulfate solution. We have our solid copper bar in a copper sulfate solution. Got a wire connecting them so electrons can flow from one direction to another. And we've got this porous barrier in the middle. Now, what is actually going to happen here is the electrons are going to flow from the zinc bar up over to the copper bar. And while it's doing that, since the zinc will become positively charged, it'll then be soluble in the water, and the zinc 2+ ions will float off into the water. And then the copper 2+ ions that are floating in water will be reduced on the copper bar and will stick to that bar. And of course, we've also got charge changing in here, right? So as this zinc 2+ is drifting out into the solution, we're building up positive charge in the solution. And as the copper 2+ is plating onto here, we're running out of positive charge on this side. So to keep the charge neutral in both solutions, our sulfate ions will drift from one side to the other through this porous barrier. Now, how do you remember which side is the anode and which is the cathode? Well, I will tell you how I actually do it. And the way I actually do it is by remembering the Greek roots for these words. So anode is Greek for a way up, and up starts with a vowel, and so does anode start with a vowel. Cathode is Greek for a way down. Down starts with a consonant, cathode starts with a consonant, and that's how I remember it. So if you look at the electrons on the anode side, the electrons are going up. On the cathode side, they're going down. And that's literally how I remember it. So you'll have to be able to draw a diagram like this, including animation. So you'll have to be able to animate that on a piece of paper, which is a joke, of course. Hopefully you got that. You'll also have to remember how to write line notation. Line notations aren't as scary as you think they are. You just need some practice. So some things to remember is all of the positive charge goes in the middle. So you'll notice the zinc is getting more positive going in, and the copper is getting more positive as it's going towards the middle. Another way of saying that is the oxidized species is always on the left, the reduced species is on the right. So even though we call these redox reactions, you have to actually write them out as ox-re. Well, you can deal with that. All right. Now these double lines here in the middle indicate a salt bridge or porous barrier, some sort of junction between the two half cells. And then these single lines on either side indicate phase boundaries or a reaction boundary. So here these are going from solid to aqueous across these phase boundaries. So a typical problem I could give you would be something like this. Draw and describe a voltaic cell using this reaction right here, where we have iron that is solid reacting with aqueous copper 2+. The copper is gaining electrons, so it's being reduced. The iron is giving up electrons, so it's being oxidized. And then label the anode and cathode, indicate the direction the electrons are flowing, indicate the way the aqueous anions flow, and write the reaction using line notation. All right, so first let's start with this bottom line. Let's write it out in line notation. Let's divide this into our two half cells. So our first half cell is going to be iron going to iron 2+, and our second is going to be copper 2+ going to copper. So which one is going to go on which side? Well, iron is going from a neutral species to a more positive species. Copper is going from a positive species to a neutral species. We're going to want these positive species in the middle of our line notation. So we'll have iron going to iron 2+, and then copper 2+ going to copper. You might be deluded into thinking that solids should go on the outside and aqueous should go on the inside, but that is a fallacy. It is not always true. All right, now let's start drawing our diagram. Let's start with some beakers. So on the left, I have a beaker with a solution full of iron 2+, and on the right, I have a beaker full of copper 2+. For these species, you also need to balance out the charge. So we're going to throw some sulfate into each side. Now, you don't necessarily have to remember which specific salts of each metal are most common, whether this would be iron chloride, iron sulfate, iron phosphate, right? So you don't have to remember the counterions, but you do have to remember to add some counterion of opposite charge to balance out the solution, because keeping these solutions neutrally charged is actually very critical for half cells to function properly. Okay, now we're going to add our solid bars to each side. So I've added an iron bar to the solution with the iron 2+, the copper bar to this side with the copper 2+, and I add a wire. And which way are electrons going to flow? Well, if we look at our reaction up here, the iron is giving up electrons and the copper is gaining them. So the electrons will be flowing this direction. Now, we should take a moment to label our anode and cathode. So which way are electrons going up? Well, they're going up this way and they're going down this way. A way up starts with a vowel, anode starts with a vowel. A way down starts with a consonant. So cathode starts with a consonant. So this is our cathode. We'll also put our negative and positive signs there too, indicating that this guy has a more negative potential and this one has a more positive potential. Now we are almost done. Electrons are flowing, but they will only flow for a very brief time and then stop abruptly. Why is that? Because we forgot the salt bridge. The salt bridge is critical for allowing the electrons to keep flowing indefinitely, or at least until this reaction burns itself out. If you don't have that salt bridge in there, what happens is electrons will start to flow, and then you'll get a surplus of positive ions on the left and a deficit of positive ions on the right, and that will just make it so the electrons don't like to flow anymore. All right, so let's go back to our salt bridge. We have some salt in our salt bridge. You don't necessarily have to know which ions are common in salt bridges, but you do have to know that it has to have a positive ion and a negative ion. Which way are these guys going to be flowing? Well, let's figure out which way things are flowing in our solutions, and that should help us get our answer. All right, so copper 2+ is going to be plating onto this copper plate, which means we're going to have a deficit of positive charge on our right side. So we're going to have to flow positive charge from our salt bridge into here. Then on our left, we're going to be spitting out positive charge into our solution, which means we'll have a deficit of negative charge or a surplus of positive charge. So we'll have to flow negative ions into this cell. All right, so you should be able to do all of that on your own. Let's look at what it looks like when I animate it. Notice the electrons flowing from the left to the right. All right, now let's say though I don't even give you a chemical reaction. Let's say I just give you two half cell reactions that look like this. All right, so I have the half cell reaction for chlorine gas getting reduced to Cl- and the half cell reaction for Cr3+ going to chromium. So in both cases, we're adding electrons to a species, and so we're reducing them. But which one of these is going to be more favorable? Well, to find that out, we're going to have to look up their half cell reduction potentials in a table. Now remember, for all of these, that negative charge likes positive potential. That means the electrons like going in the reaction with the highest potential. So this chlorine reaction is more favorable than the chromium reaction. And in fact, if you put solid chromium and chlorine gas together, you'll get a reaction that looks like this, where you have the chromium and chlorine reacting. So the chromium actually gets oxidized down to the 3+ charge state, just like in this reaction up here. And the chlorine gets reduced to the 1- charge state. And since you have a 3+ and a 1-, you'll have 1 chromium and 3 chlorines in there. Now, how do we figure out these coefficients of 2s and 3s on here? Well, we're going to have to try and balance out the number of electrons for each of these. So this top reaction has 2 electrons involved in it. This bottom reaction has 3 electrons. Now they need to both have the same number of electrons because we need to transfer all of the electrons from one place to another. We can't have electrons being created or destroyed. So we have to have the same number of electrons in each of these. So we're going to have to find the least common multiple of each of these reactions. The least common multiple of 2 and 3 is 6. And so to get there, we'll have to multiply this top reaction by 3. So that'll be 3Cl2 plus 6 electrons going to 6 Cl minuses. And we'll have to multiply this bottom reaction by 2. So that'll be 2 Cr3s plus 6 electrons plus 2 chromiums. And then we'll have to do some rearranging and adding those together to get down to this actual equation. Okay, but now that we have this reaction, let's go on to find the standard reaction potential for this reaction. So we have our reduction potentials. The way you find out the reaction potential is by taking the difference of those. Actually, there's 2 ways of thinking about this. One way is you take the reduction potential and subtract the oxidation potential. So in other words, you take the bigger number up here, or the more positive, subtract the more negative number, and you'll get your reaction potential there. You'll notice that I just subtracted here. I didn't multiply any of these numbers. For the standard reaction potential, you do not need to multiply any numbers. Okay, it's just taking the differences there. Now, one other way to think about going about getting this 2.09 value, though, is we can also think about this reaction right here with the chromium. We can think about flipping it around. And if we flip that around, then you'll notice we add this top chlorine reaction with the flipped around chromium reaction and do that multiplication of 2 and 3, we can actually get right to this equation right here. And so if you think about flipping a reaction around, then it would just be taking your redox species, adding it to your oxidized species, and you'd get the same value. Now, if that second method seemed confusing to you, stick with the first. If the first method seemed confusing, but the second made more sense, stick with the second method. Either way, just figure out a way of calculating the standard reaction potential that makes sense to you, and then stick with it. Okay, the next step is after we get this standard reaction potential, we're then going to find the Gibbs free energy of our reaction. So what we're going to do there is just take this equation right here, where G naught equals negative NF E naught. So what we have here is N is the number of moles of electrons, F is Faraday's constant, and E naught is just our reaction potential right here. So how many electrons do we have? Well, let's figure this out. So we have 2 chromiums here. In this reaction up here, we only have 1 chromium. So that means we have to multiply this whole reaction by 2, which means there's 6 electrons involved in this reaction. You can double check that with the Cl2 reaction. The Cl2 reaction, we have 2 electrons. And of course, we need to multiply this whole thing by 3, so that means 6 electrons. So in both of these reactions, we have a total of 6 electrons, and that is the number of electrons we will plug into our equation here. Faraday's constant is just 96,485 coulombs per mole. That's just a value you'll need to look up or get off the equation sheet. And then our E naught is 2.09 volts. And if you didn't know already, a volt is equal to a joule per coulomb. And so if we cancel out units here, the moles will cancel out, the coulombs will cancel out, and we'll be left with joules. We can plug all of these values into our calculator now, and we will get 21 gigawatts. So that is a soundbite from Back to the Future. That is Doc Brown saying how much power they need to send the DeLorean back to the future. Now, of course, here we have 1.21 gigajoules. It's not pronounced giga, it's pronounced giga. And we're not dealing with watts, we're dealing with joules. But that's all there is to it for finding the Gibbs free energy of the reaction. All right, the last thing that we need to talk about today is figuring out the potential generated by a cell when it's at some point in a reaction. So let's say we have this reaction here where aluminum and iodine are reacting. So aluminum is getting oxidized, it's giving up electrons, and this I2 here is getting reduced to I minus. Well, to solve this kind of question or problem, we're going to have to turn to the Nernst equation. So in the Nernst equation, on the left here, the E cell, that is going to be the potential of your cell at any given time during the process. Your E naught here, that is just your standard reaction potential. And then let's talk about the rest of this. So N is the number of moles and Q is your reaction quotient. But where is this 0.05916 value coming from? Well, it's actually coming from the real Nernst equation. So this is what the real Nernst equation looks like. Instead of this 0.05916, what we have is R times the temperature divided by Faraday's constant. And if we combine all those together, we get some constant, but you'll also notice that in the real Nernst equation, we're taking the natural log, but in this simplified one, we're taking the log base 10. Now to switch between natural log and log base 10, that's simply a multiplication factor. So we combine that multiplication factor with RT over F, and that gets us this 0.05916 value. You'll notice though that this value should change if you change the temperature. And so this value right here of 0.05916 only works at room temperature, or 25 degrees Celsius. If it's at any other temperature, you're going to have to use the full equation to figure out the answer. So let's hide that full equation for now. Let's just deal with the standard reaction, or the standard equation that we're going to use here. Let's review really fast what our reaction quotient is. So if you remember, the reaction quotient is your products divided by your reactants. And so that will look like this. We will take our concentration of aluminum. We'll have to square it because it has a coefficient of 2 in front of it. We'll take our concentration of I minus. We'll have to raise it to the power of 6 because it has a 6 coefficient in front of it. Why do we not have our reactants in our Q value? Well, let's look at our reactants here. We have aluminum and I2. Those are both solids. Since they're solids, they don't get included in the Q. Okay, so then we plug in our concentrations for aluminum and iodine that are just given in our question here. We get a Q value that looks like that. It's really small. Now we can take all this information, plug it into our equation here to find the potential. So it's going to be 2.20 volts. That is our standard reaction potential minus that 0.05916 divided by the number of electrons, which you might have to figure out by looking at the problem there, but that's going to be 6 electrons times the log base 10 of our Q. Then we get a total of 2.31 volts. All right, that's it for today. Let me know if you have any questions about any of